In this lesson, I'm going to teach you the concept of acceleration. So what is acceleration? So by the end of this video lesson, you should be able to define acceleration and state it as a unit. You should be able to describe the meaning of acceleration at greater depth. You should be able to learn how to draw a velocity time graph. And you should be able to state the significance of the gradient of a velocity time graph and the area under the graph. And you should be able to describe velocity time graphs. So let's go straight to the definition of acceleration. Acceleration is defined as change in velocity per unit time. Change in velocity per unit time. So the equation which is associated with this definition is this one here. Acceleration is equal to change in velocity divided by the time taken for that velocity to change. So in symbols, it is written like this. A is equal to V minus U over T, where A is the symbol for acceleration, V is the symbol for the velocity that the object has after time t seconds, and U is the initial velocity. So to get the change, we simply subtract the initial velocity from the final velocity to find out how much has the acceleration increased. In other words, acceleration is equal to the increase in velocity divided by time, so that we can get the rate at which that velocity is increasing. The SI unit of acceleration is meters per second squared. Now, where do we get this meters per second squared from? So this is how it comes about. Let's say maybe this final velocity could be something like 5 meters per second. The initial velocity could be 0 meters per second. Of course, divide by maybe for the velocity to change from 0 to 5, maybe it took 10 seconds. Remember here, I'm just interested with the units. So 5 meters per second minus 0 meters per second, we of course get 5 meters per second. Divide by 10 seconds. Of course, this one gives us 0.5. Now let's look at the units. We've got meters per second divided by seconds. Now meters per second is meters divided by seconds, and then that meters per second is divided by another second. So this one is like we have meters divided by seconds times 1 over seconds, and that is where we get meters divided by second squared, and we call it meters per second squared, this one here. So remember, the SI unit of acceleration is meters per second squared. To reinforce this point, let's look at an example. In this example, we are told that a moving object has an acceleration of 5 meters per second squared. Now, what does this mean? This is a very important example because by trying to understand the meaning of 5 meters per second squared, it will take us very far in trying to understand the concept of acceleration. You see, it's very easy to say that acceleration is change in velocity per unit time. We need to understand what that means exactly. So let us consider this 5 meters per second squared at greater depth. So in that question, we were given that a moving object has an acceleration of 5 meters per second squared, and we want to know what this means. Now, 5 meters per second squared means that the velocity of the object is increasing by 5 meters per second every second. The velocity of the object is increasing by this value every second. So you can see from this table, if we say that the velocity is increasing by 5 meters per second every second, suppose the object starts from rest. When the object starts from rest, it means that the initial velocity is 0. When time is 0, then the velocity is 0. After exactly 1 second, that velocity has increased by 5. So we do 0 plus 5 and we get 5. Now in the second, that is after an increase of 1 second from 5 meters per second, we have 5 plus 5, we get 10. After another 1 second, we add 10 plus 5, we get 15. After another 1 second, we do 15 plus 5, we get 20. You can see that we are going in steps of 1 second, 1 second, 1 second. And so the velocity is increasing by 5, 5, 5, 5, 5, and 5. So really this one is very simple, that when the object has an acceleration of 5 meters per second squared, it means that that velocity is actually increasing at a certain rate. The rate at which it is increasing is 5 meters per second every second. I hope this one is very clear, because it is very, very important that you do understand when you're given a certain acceleration what that means. Suppose the acceleration has a negative sign and you are told that the acceleration is minus 5 meters per second squared. This of course would mean that the velocity of the object is decreasing by 5 meters per second every second. We shall see this at a later time in this particular video. For now, let's go ahead and plot a velocity time graph, since we have a table of time and velocity. Let's see how the velocity time graph for this motion will look like. So we are going to put a graph paper in this space here, and this is the graph paper that we are going to use. I have provided you with a graph paper exactly like this one. So I've used this one in this video so that you should be able to follow it easily. If you measure the length of one box, you'll find that it is 1 centimeter, and that 1 centimeter is divided into 5 smaller sections. So we are going to start by putting this information on this graph. But first of all, we need to draw what we call the axis, the y-axis and the x-axis. We are going to put velocity on the y-axis. Of course, this one's supposed to be velocity in meters per second, not velocity in meters, but velocity in meters per second, because this one is t in seconds. So velocity will go to the y-axis because it is the dependent variable. It is the quantity which depends on time. Time is independent. You cannot slow it down. You cannot make it move faster. So it is independent. But the velocity changes with the time this way. For example, after every second, the velocity increases by 5. We may have another situation whereby after every second, the velocity increases by, say, 2 or even 3. So really you can see that the velocity in meters per second is dependent on time. So let's draw those axes, with the y-axis being for velocity and x-axis time. And here we've got our axis. So the first thing we do is to try and see whether our values in the table will fit. And you can see that since the maximum velocity after 6 seconds is 30, we can move in stages of 5, 5, 5. That one will be a comfortable interval. On the t-axis, we could have chosen another scale, but I thought this one would also be suitable. You know, anything which is legible and can allow us to plot this graph neatly would be welcome. Now, the next thing is, or before you go to the plotting of the points, I'd like you to note that every time you draw a graph, you must label the axis with the quantity and the unit. So remember that V is the symbol for velocity. Meters per second is the unit of velocity. Very important. T is a symbol for time and second is the unit of time. So remember, the axis must always be labeled with the physical quantity and the unit of that physical quantity. Now let's go right ahead and do the plotting. Now the plotting is done this way. When time is 0, velocity is 0. So we ought to have plotted this point here. When time is 0, velocity is 0. When time is 1 second, velocity is 5. So we look at that point where the two intersect. When t is 1 and 5 and v is 5, we come this way and we also come this way. Wherever they meet, we put an x. When t is 2 seconds, from the table you can see that the velocity is 10. So again, where 2 and 10 meet or intersect, we put our x. We continue like that until we have plotted all the points as they appear in the table. So when we put an x at the intersection of this x value and the y value, you have plotted that particular point. The next point would be to draw a straight line along these points because you can see they are in a straight line. So you draw a line joining all the points since they are in a straight line. It's not always that the points will always be in a straight line. Sometimes they can be in a curve. But in this case, if you put a ruler along these points, you'll find that all of them will lie on a straight line. So you join them using a straight line using, of course, a ruler. At this point, I'd like us to think about how we can calculate the gradient of this graph. By gradient, we are supposed to draw a right-angled triangle that connects any points. Let's say, for example, I choose this point here. So I would draw my right-angled triangle from this point, come like this, maybe reach that point. From here, I would go upwards like that. So I can draw a right-angled triangle anywhere along this line. And I will say that this one is change in the quantity on the y-axis, delta V. This is change in the quantity on the t-axis, delta T, like that. So delta is a symbol that is used to represent change. So over here, I will come and state this. Gradient of the graph is going to be equal to change in the quantity on the y-axis divided by the quantity on the x-axis. So delta V over delta T. And we'll be able to see that when I get that change, you can see that this point here corresponds to 20. The value of y is 20 meters per second. So I'll write here 20 meters per second minus this other point here will correspond to 5 meters per second. The change in time will of course be from 1 all the way to 4. So I'll do 4 minus 1 in order to get this change. 4 seconds minus 1 second. And you can see this one will give me 15 meters per second divided by 3 seconds, and I'm going to get 5 meters per second squared. Now we learned something here. The gradient has the unit meters per second squared. We have just learned that the unit for acceleration is meters per second squared. We end up making a very strong conclusion here that the gradient of a velocity time graph is equal to acceleration. Very, very important. Acceleration. The gradient of a velocity time graph is equals to acceleration. Of course, at a later point, we are going to see that the area under the velocity time graph will represent the displacement of the object. But for now, let's get satisfied by just calculating the gradient of that straight line, because at this particular point, we have just drawn the velocity time graph, and now we are interested. We want to know, what does the gradient of the velocity time graph represent? Now, when we study this graph, we would be able to see that for every second, the velocity increases by 5, because we simply need to check here. This is 1 second. How much is the velocity? 5. In the next 1 second, meaning the second, how much is the velocity? It's 10. How much has it increased by? It has increased by 5. Now let's check in the next 1 second, that is from the second to the third second. And in the third second, the velocity happens to be 15. In the previous 1 second, it was 10. How much has it increased by? When time increases by 1 second, we find that the velocity all the time is increasing by 5 meters per second. That one's very, very important. And this further reinforces the fact that when you are given a certain amount of acceleration, it tells us by what value does the velocity increase every second. Now, supposing we're given another type of graph. This is the graph that we have just drawn. Supposing we are given this type of graph, is it possible to tell or to determine the rate at which the velocity is increasing? Let's check. In the first 1 second, the velocity of the object is, this must be 2.5. It is exactly between 0 and 5. So, the velocity has increased from 0 all the way to 2.5 in 1 second. So, in the next 1 second, meaning the second, the velocity has increased by a further 2.5. So, 2.5 plus another 2.5 gives you 5. In the next 1 second, that is in the third second, the velocity is 7.5, because again it is between 5 and 10, 7.5. So in 1 second, the velocity has increased by a further 2.5. We can see that at this point, the velocity is increasing by 2.5 meters per second every second. I'll repeat that because it's very important. The velocity is increasing by 2.5 meters per second every second. So how much do you think is the acceleration? That statement that we have just agreed upon is the acceleration of this object. If the object's velocity is increasing by 2.5 meters per second every second, it means that the acceleration of the object is 2.5 meters per second squared. Very, very important. Now, let's look at this. So you can see this obviously has got a smaller gradient compared to this one. You can see it is less steep, and consequently its acceleration is small. If you have to calculate the gradient of this line here, you will find that it is 2.5 meters per second squared, while this one was 5 meters per second squared. So when we look at graphs, even if the values are not given, we can be able to tell which one has got a higher acceleration. We just need to look at the gradient. Which one is the steepest? This is the steepest, so it must be having the highest value of the acceleration. While this one is less steep, so its acceleration is less than this. We can use the same argument to tell that this object here has a higher acceleration than the one we plotted earlier. Can we be able to prove this? Of course, yes. Look at the rate at which the velocity is increasing. In the first 1 second, the velocity increases from 0 to 10. In the next 1 second, it increases from 10 to 20. And in the next 1 second, it increases from 20 all the way to 30. So you can see the velocity is increasing by 10 meters per second every second. And that means the acceleration of this object is 10 meters per second squared. So I want to repeat this point because it is important. For you to tell which object has got the highest acceleration, you just need to consider the gradient. Which one has got the highest gradient? The one with the highest gradient must be having the greatest acceleration. Let's go ahead and consider other types of graphs. We can draw a graph which looks like this. In fact, we can draw any type of graph on this page. If a graph has got this shape, let's try to find out how much is the initial velocity of this object. And by initial velocity, we know the velocity it has when time is 0. So we check here. When t is 0, you find that its velocity was 30 meters per second. Now when t is 1 second, its velocity has become 25 meters per second. So you can see that unlike the other three graphs, over here, as time increases, the velocity is decreasing. And you can see it is decreasing at a rate of 5 meters per second every second. And this is what we considered when we were looking at an acceleration of minus 5 meters per second squared. This means that this is minus 5 meters per second divided by 1 second. It means that the velocity of the object is decreasing by 5 meters per second every second. If we were to get the gradient of this line, the first thing we will realize is that it has a negative sign. The gradient has a negative sign, and that means that the acceleration has a negative sign, and that further means that the velocity of the object is decreasing by a certain value every second. When the acceleration of the object has a negative sign, we refer to it as deceleration. A deceleration. So the deceleration of this object is 5 meters per second squared. Now let's go ahead and look at another type of graph. We can have this, a curve this time. It's not a straight line. What do we know about curves? We know that if we are given a curve which curves upwards like this, its gradient is increasing. And if the gradient is increasing, it means that the acceleration of that object is not constant. It is increasing. This is another very important point. When we are given straight lines, they've got constant gradient or uniform gradient. The gradient may be positive or negative. The fact remains that since it is a straight line, the gradient has a uniform value, has a constant value. And that means since the gradient represents acceleration, all these objects, this one, this one, this one, and this one, have got an acceleration which is uniform. It may be negative or positive, but it is uniform. In other words, this velocity is decreasing by 5 meters per second every second, while this one, the velocity is increasing by 5 meters per second every second. That increase in velocity is uniform. It has a constant value of 5 meters per second. When the graph is a curve, the gradient is not constant. In fact, the gradient is increasing. We end up concluding that this is an object whose acceleration is increasing with time. The acceleration is increasing. But this other graph here, the acceleration is uniform or constant. Very, very important. So each and every time you're given a velocity time graph, please try to think about gradient. What does the gradient represent? And then, how is the gradient changing? Does it have a uniform value? Or does it have a value which is changing? Does it have a value which is positive or a value which is negative? Those are the key points that you need to consider when you are looking at velocity time graphs. Because one of the questions will be for you to be able to describe the motion of an object when you're given its velocity time graph. Let's consider the last graph, which is this one here. In this graph, definitely we can see that the velocity is not changing. The initial velocity was 15 meters per second. After 1 second, it is still 15 meters per second. After another 1 second, it is still 15 meters per second. So this is how we can tell that this object is moving with uniform velocity. Uniform velocity, that is constant velocity. For the other graphs, the velocity is changing. But here it is not changing. It remains 15, 15, 15 throughout. For example, here, the velocity was increasing by 5 meters per second every second. Here it was increasing by 2.5 meters per second every second. While here, it was increasing by 10 meters per second every second. Here, it is decreasing by 5 meters per second every second. The fact remains that in this graph, this graph, this graph, this graph, the velocity is changing, and it is changing uniformly. Over here, the velocity is increasing, fine. It is increasing with time, but the rate at which it is increasing is not uniform. Again, since we are comparing this graph with the other graphs, we notice that here the velocity is not changing, while in the other graphs, it is changing. It may be increasing at a uniform rate, decreasing at a uniform rate, or increasing at an increasing rate. Let's stop this lesson at this point so that you can have time to look at the video deconstruction document that I've made especially for you, so that you can be able to internalize the concepts that we have learned here. So if you've not joined my online class yet, make sure that you send me your email so that I can include you in my online class, where I'll be able to give you assignments from time to time so that you can internalize any concept which I teach in that particular class.